Okay, so as promised, we're going to apply Gauss's law to see how useful it really is. The first type of application, once again, high symmetries. Okay, high symmetries. We look at three types of high symmetries: spherical symmetry, cylindrical symmetry, and planar symmetry. For all these three cases, there is enough symmetry in the problem so that Gauss's law can be simplified. The calculation of this integral can be simplified if you choose a surface in the right shape to reflect the symmetry of the problem. Okay, so let's look at spherical symmetry first. There is something called Newton's shell theorem from Physics 1b. I don't know if you recall that. What does Newton's shell theorem tell us? It has to do with the gravitational field, but once again, the gravitational field and electrostatic field, they share the same inverse squared nature. So really, in this particular respect, if you prove one, you can prove the other. What does Newton's shell theorem tell us? It tells us that if you look at a uniform spherical shell, okay, mass distribution uniform, then the gravitational field outside this uniform shell is equivalent to the field of a single point mass located at the center of the shell, with all of the mass of the shell crushed onto it. So, in other words, if this is a space probe outside, if you're inside a space probe, and you try to figure out, is this a uniform empty shell of mass, or is this a solid shell? You cannot tell any difference. Okay, if it's a uniform shell, if it's a point mass at the center, you cannot tell any difference. Okay, because it behaves as if it were just a point mass. That was part of Newton's shell theorem. The second part of the shell theorem says that once you dig a hole, okay, you go into the empty shell, no matter where you are, you don't have to be the center, no matter where you are, as long as you're inside, what is the net field? The gravitational field. It is zero. Okay, that is the second part of Newton's shell theorem. We used it in Physics 1b, but we did not really prove it because we didn't have to go through this integral. But now we don't have to work out a nasty integral. We can prove it very quickly. Okay, we're going to do it in the case of Coulomb's law, but again, it's equivalent to the gravitational force in this case because both are inverse square. So let's look at how we calculate the electric field of a spherical symmetry case. By spherical symmetry, I mean the density, okay, the charge density is not a function of theta and phi, these angles, right, the orientation. It is only a function of r. What's r? R is the distance from the center of symmetry, okay, say the center of a sphere. So again, the distribution of charge has nothing to do with directions. It only has to do with how far you are from the center of symmetry. Say a point P, a distance r from the center. Rho is a function of r only at point P, not a function of orientation. I can show that with this kind of symmetry, one can calculate the electric field anywhere in the problem with great ease. Now, to reflect the symmetry of the problem, what kind of Gaussian surface should I choose? Gauss's law tells us that you can always get phi equals to Q enclosed over epsilon naught, no matter what surface do you choose. But of course, we're not going to choose just any surface. We're going to choose a smart surface, right? Now that we have the freedom to choose whatever surface we want, we're going to choose a surface that reflects the symmetry. So what kind of surface do you think you have in mind? Well, why don't we choose a surface that reflects the symmetry by drawing a sphere? Okay, suppose we want to calculate the electric field at point P, a distance r away from the center. Now, in order to do so, I must draw a Gaussian surface passing through point P because I want to know the electric field at that point, right? And I want to draw a spherical Gaussian surface. So it's a spherical Gaussian surface centered at point O, but passing through point P. In other words, radius is r. Alright, so this Gaussian surface, the integral can be written as this: E dot dA over the Gaussian surface A. Okay, that's the particular Gaussian surface we choose. We're not going to choose a cylinder or any weird shape. We're just going to choose a sphere. Now, how does the symmetry help us simplify this integral? Well, first of all, because of the symmetry of the problem, the electric field points outward like this. I'm assuming the rho is positive. If rho is negative, it just point inward, which is also very simple. Okay, E points this way, so does dA. Right? dA also points this way. So the first step is E and dA. They have the same orientation, therefore I can write this as just E dA. Okay, because the angle theta between them is 0, so cosine 0 is 1. That's the first step. And the second step, you'll notice that this electric field, here's the magnitude of the electric field E. That magnitude is the same everywhere on that Gaussian surface, right? Because that's the symmetry of the problem. The symmetry of the problem. So E has the same magnitude, and therefore I'm going to take it out of the integration. So this is just E. I'm going to be taking it out. dA. Now, what do we do next? All we have to do is to integrate over dA over the entire Gaussian surface. That's just a sphere of radius r. We know exactly what to do. Okay, so this really is just E times 4 pi r squared. There we go. But wait a second, isn't that equal to Q enclosed over epsilon naught? Gauss's law. Okay, and then you can see I can easily solve for E now. I just move that 4 pi r squared over to the other side, and I get E equals to, okay, move that over, Q enclosed, actually 1 over epsilon naught, and then there's 4 pi here, so 1 over 4 pi epsilon naught, Q enclosed over r squared. There we go. Okay, and this looks very familiar. That's just K, right? 1 over 4 pi epsilon, isn't it just K? Just K cubed over r squared. That looks like the expression of a point charge. Okay? That is why if you observe this charge distribution from outside a sphere, okay, and if the charge is uniformly distributed inside the sphere, then when we look at it from outside the sphere, it behaves as if it were just a point charge located right at the center, because that distance is r. You crush all the charges right at the center. You will get exactly the same electric field there. That, in fact, is part of Newton's shell theorem, isn't it? And if you wish to express into a vector expression, all you have to notice is that the direction of E field is really out. So I'm going to just add a unit vector like this, and this turns into a vector expression. Okay. So it's very, very simple. It's just like a point charge. Of course, one has to calculate the expression for Q enclosed. Sometimes it's very simple, just add all the mass, all the charges up. Sometimes the calculation of E enclosed is not that simple. So let's take a look at some special examples of spherical symmetry. This is the general expression for spherical symmetry. The only thing you have to do, really, is to calculate how much charge is enclosed. Enclosed by what? Enclosed by the Gaussian surface, okay, of radius r. So let's look at the first example of uniform spherical charge distribution. So we have what's called a uniform shell. That really is just an electrostatic version of Newton's shell theorem. All right, uniform spherical shell. So we have charges distributed evenly on the surface of this shell. There's no charge inside the shell, and there's no charge outside the shell. Just uniform distribution on the surface of the shell. Okay, and I wish to plot the electric field as a function of r. R is the distance measured from the center. Okay, the general formula, again, is Q over 4 pi epsilon naught r squared. And that Q is the charge enclosed over the Gaussian surface. The first thing I'm going to do is I'm going to calculate the electric field somewhere inside the shell. Okay, somewhere inside the shell. And let's say this point. If you wish to calculate the electric field of this point, what kind of Gaussian surface should you be drawing? You should draw a Gaussian surface passing through this point, right? And then it has to reflect the symmetry. So, that will be the Gaussian surface. So tell me, over this particular Gaussian surface, how much charge do you enclose? Nothing, right? Because it's empty inside. So charge enclosed is 0. So therefore, what is the electric field inside at that point? Well, it's zero, right? No matter where that point is, as long as it's inside the shell, you don't enclose any charge. So the electric field remains zero from here to there, just like the gravitational field of a uniform mass shell should be zero inside that shell. So the electric field is zero. That is another part of Newton's shell theorem. So zero all the way here. Now, what if you're outside? You are here. You look for the electric field. Okay. It's same thing, Q over 4 pi epsilon naught r squared, except this Q is now the charge enclosed by that Gaussian surface. Now that Gaussian surface encloses everything, right? The charge enclosed is no longer zero, but rather just the total amount of charge Q. Alright? And therefore, outside the Gaussian surface, the electric field jumps abruptly to kq over r squared, or q over 4 pi epsilon naught r squared. So it jumps. Right? And it's inverse squared, like this. This expression is q over 4 pi epsilon naught r squared. Okay, so this is really a reflection of Newton's shell theorem in the electrostatic case. And you can see how quickly we obtained this result. If you want to calculate this result based on Coulomb's law directly, then whether inside or outside, it's going to be a nasty integral, right? For example, if you look at for the electric field here, then you're going to cut this into pieces, many pieces. Each piece have a different, will produce an electric field in a different direction, different magnitudes. So you're dealing with a nasty three-dimensional integral, and it's not nearly as desirable as our new method. Okay, another thing I want you to notice is that there is a sudden jump in the electric field. You wonder, when does the electric field go through a sudden jump? It must be some very strange location. What's so special about the shell? Because it happened right across the shell, right? Right inside the shell is zero, right outside the shell it jumps to q over 4 pi epsilon r squared. So what's so special about that? Well, what's on the shell? On the shell you have a layer of charge. It is not a three-dimensional distribution. Rather, all the charges are crushed onto a very thin two-dimensional charge. So you can see that there is a sudden jump in the electric field when you go across a two-dimensional or surface charge distribution. Okay, this is when you see a sudden jump in the electric field. So here we scored our first elegant application of Gauss's law. We obtained this result without any complicated integration. Now naturally, the next thing you want to look at is a uniformly charged sphere, a solid but uniformly charged sphere. It is no longer a shell anymore. Alright. But it's still spherical symmetrical, so we can still calculate the result based on Gauss's law. So suppose you're outside, okay, suppose you're somewhere here. What is the electric field there? Well, it's again 1 over 4 pi epsilon naught q over r squared, and that q is the charge enclosed, the total charge enclosed. Does it matter whether that charge is on a surface or is uniformly distributed? No, it doesn't. As long as it's spherical symmetrical, you get exactly the same result. So what is that telling you? It tells you that outside the shell, the electric field remains the same as if the shell were empty, and as if it was just a point charge in the middle. Okay, so this is 1 over 4 pi epsilon naught q over r squared, just like before. You cannot tell by looking just outside. You cannot tell whether this sphere is solid or hollow, as long as it's uniformly distributed. Okay. But what's interesting is what's inside. Suppose you want to know the electric field at this point, okay, somewhere inside the sphere. Again, you have to draw a Gaussian surface, the red one, that's the Gaussian surface. But what is the charge enclosed by that Gaussian surface? Is it zero anymore? No, not quite, right? It is the charge enclosed by this region. Let's say the total charge enclosed by the entire green sphere is big Q. Then how much charge is enclosed by this red Gaussian surface of radius small r? Well, if it's a uniform distribution of charge, then we know that the charge enclosed, okay, Q enclosed, is a fraction of the total charge, and the ratio is like this, right? Q enclosed over the big Q, right? And that ratio should be what? The volume of this region over the volume of the entire region, right? Why is Q proportional to volume? Because the charge density is uniform. Right? That's our assumption. So it is equal to 4 pi over 3 times small r squared. It's actually small to the power 3. That's for this volume. And for big Q is 4 pi over 3 times big R to the power 3. So really it's just small r over big R to the power 3. If you cancel 4 pi over 3. Right? So that's the ratio of the volume. Here's the ratio of the charge. From that I can calculate Q enclosed. And therefore, the electric field inside the sphere, okay, the electric field inside the sphere, I can write it like this. E equals the general formula 1 over 4 pi epsilon naught Q enclosed, alright, over R squared. Isn't that the general formula? Okay, and that equals to 1 over 4 pi epsilon naught R squared, and then copy that formula, okay, as big Q times R to the power 3 divided by big R to the power 3. You do a little simplification. Okay, you do a little simplification. Here's R to the power 3, here's R to the power 2. So they cancel with 1 power left. It's Q over 4 pi epsilon naught, big R to the power 3, the whole thing multiplied by R. Interestingly enough, you get a linear field. Okay, the electric field inside the sphere is not zero, but it's linear. It starts from zero in the middle and extends uniformly out, linearly outwards. On this diagram, how should I draw it? Well, it's a straight line, right? Because it's proportional R to the first power, starting from 0. Where does it end? Does it meet that point? Well, let's see here. As small r equals big R, so we're right on the surface here. You replace small with big R, what do you get? Well, you get Q divided by 4 pi epsilon naught and then times big R to the power 2. But that's the same as that expression when small equals big R, right? Q over 4 pi epsilon naught big R squared when small equals big R. So what does that tell you? It tells the electric field right outside the sphere and right inside the sphere, they are actually the same, okay? So there is no discontinuity this time. This is the electric field distribution for uniformly charged sphere. There is no discontinuity of the electric field, unlike the previous case when you saw a sudden jump. Okay, when you saw a sudden jump across the boundary of the sphere. So why do we not have a sudden jump in the electric field? Because what's on the outer surface? What's on the surface? Well, nothing. Okay, there is not a layer of two-dimensional charges concentrated and crushed onto it. Rather, it's just a three-dimensional charge distribution. So when you go from a point immediately inside to immediately outside, you don't really encounter a lot of charge at all. So therefore, the electric field should not suddenly jump. It should be continuous. This linear electric field is an interesting thing, because suppose I dig a tunnel. Okay, suppose I dig a tunnel and I put a negative charge inside, say an electron. This electron will then experience the electric field, electric force that is linear, because the field is linear. Okay, you have a linear force pulling you into the center, a linear restoring force. What is that? How does that ring a bell? What does that tell you after you study physics 1B? When you experience a linear restoring force, what kind of motion are you going to execute? Simple harmonic motion, right? Okay, so if you dig a tunnel, you put a negative charge there, you put it anywhere inside, and let go of it, what's going to happen? It's going to go back and forth, back and forth, back and forth. Simple harmonic motion. Now you recall in physics 1B, we learned that if you dig a tunnel inside the Earth, assuming the Earth were to be a uniform sphere, and you dig you drop a package into the tunnel, it's going to accelerate toward the Earth and then decelerate, appear on the other side, and if you don't retrieve the package, it will keep on going back and forth in a simple harmonic motion. It's the same as that case. Okay, because gravitational force and electrostatic force both satisfy inverse square law. So if you were to draw the gravitational acceleration in the electric field of a uniform spherical mass, you're going to get the same exact expression. Okay, linear field inside and a 1/r squared field outside. So this is a neat similarity between these two great forces.